Hello everyone, this is Deepthi, and in this video I will be explaining about minimization of DFA. So first let's see what is minimization. As the name itself suggests, minimization is nothing but converting the given DFA into the equivalent DFA but with a minimum number of states. So we can achieve this using two ways. One is using a equivalence theorem and other is using a Mahil-Nerad theorem. And in this video I will explain how to reach minimized DFA using equivalence theorem. So let's first see the steps involved and then we'll get into the example. So the first step is to eliminate all the dead and inaccessible states. So what exactly is dead state? Dead state is any non-final states which transit to itself for any input, and inaccessible state is the one which can't be accessed using a initial state. So we will remove those and then go into the step two. In step two, we write a transition table for the given DFA, pretty simple. Then the most crucial step is step three and step four. In step three, we will divide the given transition states into two sets. So one set contains all the non-final states and other set contains all the final states. And in step four, we again divide this set into different sets. We consider all the possible pair of states in each set. And if the two states are distinguishable in the sense if they reach different states for the same input. Let's say we have Q0 and Q1 in a set and we give them input 0. If Q0 reaches Q2 and Q1 reaches Q3, then we call them as distinguishable. So in those cases, we again partition the set into different sets. And we go on doing this process until there is no change in partition occurs. And now in the final step, that's step 6, we have all those states which belong to the same set are equivalent, so we can combine them and form a single state. So now let's see the example for better understanding. We will solve this problem. So first, we have to check for all the dead and inaccessible states. So we can't find any inaccessible states. We can reach all the states using Q1, Q0. Q0 is the initial state. So yeah, we can reach all the states using Q0. And then let's move on to step two. In step two, we draw a transition table. So for Q0 reaches Q1 on getting input 0. So we have written that, and Q0 on getting input 1 reaches Q3. So in this way, we have written the transition table. So let's move to step 3. So in this step, in P0, we can see here that Q4 is the final state. So Q4 is in a different set and all the other states in one particular set. Now let's take the pair of states in each set. Let's now take Q0 and Q1. So Q0 reaches Q1 on input 0 and Q1 reaches Q2 on input 0. Both Q1 and Q2 are in the same state, so no issues. Now let's take input 1. So Q0 reaches Q3 on input 1 and Q1 reaches Q4 on input 1. So Q3, and as we can see here, Q3 and Q4 are in two different sets. So Q0 and Q1 become distinguishable. So we now take Q0 in a different set. So we partition the set. Now let's take Q1 and Q2. So Q1 reaches Q2 on input 0 and Q2 reaches Q1 on input 0. And both of these are in the same set, so no problem. We again do that for input 1. So Q1 reaches Q4 and Q2 reaches Q4, no issues. Now let's take Q2 and Q3. So Q2 reaches Q1 on input 0, Q3 reaches Q2 on input 0. And as we can see here, Q1 and Q2 are in the same set, so no partition. Now let's take for input 1, Q2 reaches Q4 on input 1 and Q3 reaches Q4 on input 1, so no issues. So there is no change in partition from P1 and P2. So these are our minimal states, and this is our minimal DFA looks like. Thank you for watching.